All right, week 128 of building my own operating system. Thanks a lot for joining. Today, we're working on scheduling some more. Um, in general, that's been the topic for a while now. And what I want to get back into today is task waiting, kernel tasks waiting on other tasks. Before I dive in, I want to do a quick sponsor shout out. This stream is sponsored by myself. I have a small favor to ask you if you're watching this stream. So, one thing I would really like to talk to you about your challenges in the world of systems programming. I'm trying to figure out how I can be more helpful to my audience of systems programmers, and I want to hear about the challenges you have going on in your life. Anything related to that, whether it's technical, career, or otherwise, I'd very much like to talk to you about that. You can contact me if you're interested. Here's all my information: Discord, my Instagram, and my email. So, with that said, let's get into the stream. Okay. As usual, going to give a quick test in the chat. Hello, Code. What is up? First one in the chat today. Actually, you're making me realize that I did not do a post in the Discord yet. Streaming now. More kernel task waiting. All right. What's up, Sarab? Hello, hello. Some nice people in the chat today. Thank you for the hearts. Yeah. Let's slowly get into things. I have to leave pretty promptly in 2 hours, so I'm gonna try to make the most of the time in today's stream. As usual, let's just begin with a little bit of a warm-up. Yeah, let's just do a bit of a warm-up. We'll see what the warm-up is. Yeah, I think it's today, 12th. The warm-ups, yeah, what's the warm-up? We're gonna need to understand what was going on previously. We were working on all this waiting stuff previously. So, what's up, Narajan Dada? You'll have to give me a tip on how to pronounce your username. Nice to see you again. We were working on all this waiting stuff, and I want to keep working on this. I have some other ideas about how to approach this, so yeah. That's the general roadmap. Some kind of, yeah. All right, I'm just gonna get into things. So today, task waiting on other task. Idea. Try inverting the implementation. Instead of task storing pointers to tasks, it is waiting on, which I think is how we did it last time. A task stores pointers to tasks that are waiting on it, which is the other way of doing things. And I was having some conversations with with some LLMs about my OS, and it seemed like this would be a good implementation to try. Could have some advantages over the previous implementation. So let's just get into this. Yep. So do a little bit of a build. We're building what does the history look like? So it has all this stuff we were doing previously. I was sort of messing around a little bit. I think this is one of the main things. Yeah. So we update waiting tasks. Yeah, so previously the way the task waiting worked was, let's just jump into the code. Scheduler.hpp. So, wow. Oh, as usual, I'll get my time, my 20-minute timer going. What's up, Ray? Early Sunday stream. That's true, absolutely. I got some plans later this afternoon, so I can't make my usual time, so. Oh. Excuse me. Yeah, I have some plans a bit later, so gotta move it up a little bit. Yeah, hope you're not awake at like super early in the morning, 6 a.m. or something like that. Shout out if you are. Okay, let's walk through this step by step, just to warm up a little bit. So let's talk about the wait test. So this is just a simple kernel task that all it does is it creates another task and then it waits for it to exit. Yeah, apparently it's dangerous to use ptask after this point because it has exited, so that is orthogonal to this topic. 11 for you. Okay, nice. Okay, cool. Good to know. Yeah, so that's sort of this little test, and that's how I'm testing this wait for exit API, which is new in the scheduler and allows a task to wait on another task to exit. Task wait for exit. And what's up, Rahul? You're awesome. Thank you very much. Estimate time when I can use this OS on my computer. Oh man. Don't get your hopes up. But maybe you'll be able to use it to develop some OS stuff of your own at some point. I think that's a bit more realistic. Okay. So this is how it looks currently. So we just do a really basic check. Is the task already exited? In that case, we can just return immediately. Otherwise, we like actually enter this thing. And why do I have some squiggles here? No task waiting on. Okay, I think my playing D tends to get just messed up for some reason. Okay. And the idea is, okay, currently a task stores a container of things it's waiting on. It's really only tasks, or so you can only wait on tasks for the moment. So it's like a task maybe it's waiting on a couple different things. So it's storing some pointers to these things that it's waiting on, with the idea that we can kind of go through tasks and check the states of these things that we're waiting on at periodic points, and then see if we need to change things. So that's how this looks. So we just assert that the container isn't full because that's how I'm doing things currently, static containers. And then we append to this list with a pointer to the thing that we're waiting on. And then we yield ourselves into a waiting state, and we go into task yield, which yields ourselves and kind of basically blocks this task from running because it's in a waiting state. And this should all be fairly visible. In this collection of diffs. Yeah, here's where we add the state. Scheduler, HPP gets some new stuff. Gets this part. The counterpart. So this is one half of the equation for waiting on another task. It's like, okay, this is the part where a task puts itself to sleep, basically, when it goes into the waiting period. The other part is, okay, who's going to wake up the task? What's that look like? And that, in this implementation, that happens over here. On every schedule or reschedule, we sort of hook that event, just that schedule opportunity, and we call this update waiting tasks. And this is just this function that just goes through and checks all of the waiting tasks if a waiting task should be converted into a runnable task. Give me 1 second. Right, and so I am opting to use some C++ features, which I don't know if they help. I think they might help. They also somewhat obscure the logic, but it's like first of all, I'm filtering all of the tasks to only get the waiting ones, which is ultimately still going to be a linear time operation to go through all the tasks. And so that's not necessarily the production implementation. I think production OSs often optimize this by keeping specific lists per state. So a list of only waiting tasks, which allows you to iterate only the waiting tasks efficiently, as opposed to iterating all tasks and searching for the waiting ones. But yeah, this is just sort of, oh damn, sorry about that. So yeah, this is just, we'll get the waiting task. Then for every waiting task, that it's waiting, and we're going to remove any tasks from this waiting container if they have become exited. And we get the number that were removed, and if any were removed, we set our task state back to runnable, which now makes us eligible to be considered by the scheduler. So yeah, what's up, Demona? Yo, bro, keep going, thank you. Make sure it can run exe. What's up, Nurbeck? What do you think about AI agentic coding? I think there are a lot of really useful use cases for AI and agentic coding, but But as with any new technology, you can overdo it and it also creates new problems. So we just need to be aware of those. But in general, I am pretty optimistic. I think a lot of, can do a lot of great things, but yeah, we need to be careful to compensate for the downsides. One downside being just getting stupider because no one knows how to think anymore. Okay. This is an implementation, and that's basically all there is. It's like this is like one side of it. This is like the waking side, and this is the waiting side. And that's fundamentally all there is to it. However, I sort of was exploring this 2 weeks ago from a suggestion, but I would like to, this is not the only way to implement this, and I think what I have understood from the LLM is maybe there's a different implementation that's better. And specifically, rather than the task taking pointers to things that it is waiting on, it's sort of the other way around. The thing that has a bunch of things waiting on it has pointers to everyone waiting on it. And I'd like to prototype that. What's up, Nico Lowe's? Do you use Codex Claude Code? Yes, definitely. Yeah, we totally might end up using it this stream also. So, yeah, I'm getting pretty into Claude Code these days. Yeah. Although I've heard Codex is pretty good too these days. I think I used it in the past and it didn't quite feel as good, but maybe they've probably improved it a lot. So I think that's mostly it for this diff. Did some cleanup. Yeah. So let's try a different way of doing things. Sort of trying to figure out the best way to do that. I think I might make a branch. First of all, I think I might squash a lot of this stuff. Yeah, the thing is, I sort of I have all these experiments going, which I kind of want to preserve. But I think so. This was. Let me just clean up my Git a little bit. This is almost too messy to even work. Move kernel. Dynamically allocate storage for kernel. Okay, cool. Whip, use test 0. So scheduler, this thing, and then I think the work sort of starts here. That's where we start to add this list thing. Even this, somehow this is in this commit. So I think I'm just going to go ahead and I'm just going to squash pretty much all of this stuff down into this commit. Or something like that. Okay, separate branch, dude. Yeah, I just haven't had any time at all to clean up my branches. I'm sort of living in this massive mess, but what let me even see. I want to branch off at some point. So maybe it was a bit aggressive. So I'm going to even separate this out into a different commit. So this ETL return num removed from list remove if, right? So I actually should be separated out. These are genuinely some useful things to have around. Is just adding some helpful little tests. So test wait test tasks wait test and nope task. So that comes out. So then what else is here? This is kind of irrelevant. Let's move this out. So this is just some whip stuff. I'm just trying to like sort of clean this up to nail down really the core of what this thing is all about. So these two are just sort of like these whippy, like changing basically the kernel run for what the kernel runs. And now we're sort of really nailing down specifically the changes relevant to this feature. There's a bit too much in this commit actually, but it's a little bit, yeah, it's a little bit tangled up. Technically this unmapped garbage stuff doesn't really belong. Some weird ideas I had. Okay, let's I think I'm in a decent enough place to try to, I basically just wanted these things also. Now I can decide how I want to do it. Okay, you know what, just for the sake of being able to move forward, I'm just going to make a branch off of here. We'll call it task wait invert impl, because we're sort of inverting the implementation. And here's what we want to do. So just to start off, I want to make sure my kernel.cpp, I want to make sure we're running the wait test. Right, so this is going to cause us to execute this. And hopefully we should, if we just even run the kernel right now, it should be working. We should see this panic, right? So let's just make sure we're in a sane state. Panic, succeeded and resumed execution, so good. So we're in a sane state. We actually have it working, but then the idea is to iterate and refine this implementation. And what I'm talking about is restructuring this part. And so instead of a task, waiting task, another waiting task. Actually, yeah, wait, this is actually, right. These are the illustrations of the two ways to do it. Here is how we're currently doing it. A task that's waiting has a bunch of pointers to these other things that are being waited on. So, right, that's how we're doing it right now. I want to flip it around and just see how that would look. So basically, this is more the idea. It's like waiting task, waiting task. This thing is being waited on by a bunch of different entities. And on the exit event, this thing can go and just go through this list and update all of them pretty much unconditionally, I think. I guess it sort of depends on the semantics of how they're waiting. But like, for example, if this is waiting on, this could be waiting on multiple things, and maybe it only wants to wake up when all of them have become available or something like that, as opposed to like only one of them becoming available. So that is, yeah. That's maybe a future complication, but for now, let's just keep it really simple. And so the way it's going to look is task. It's basically a similar thing, except the name, it's like the naming just kind of changes. It's like, it's no longer waiting on, it's sort of like the waiters. So a task now stores pointers to the tasks that are waiting on it, waiters, right? So now it's going to affect this. I think it's going to be kind of similar, and I think the AI even is suggesting it already. As usual, I just like to keep the comments around just so I can compare the before and after. And so it's really, what we want to do in here is we actually want to queue things into the task to wait for. And so the task, we're just sort of flipping everything around. And so, yeah, current task. Ooh, sorry. There we go. And so now what we've done is a task is trying to wait on something. And then now the task we're waiting for, I think the terminology is like always kind of confusing. The task we're waiting for this thing to exit, starts to record, remembers us as the current task. And then the same thing, we still go into a wait, we yield ourselves into a waiting state. That's not different. But this part is the only thing that changes. So that's the first half, right? Right, there's two halves to the implementation of the waiting and stuff. And so, right, here's the old world with the two halves, and here is our new implementation. All the way, task stores pointers to everything it's waiting on. Old way, new way. Task that is being waited on stores pointers to everything that's waiting on it. Thinking. Yeah, I'm just trying to explore how these two different implementations feel. So yeah, this is wait side, wake side, right? These two sides of the implementation. What's up, Bleh? You inspire me to build something great beyond what I'm doing at my job. That's awesome, man. Yeah, I know you have it within you. Just gotta put in the work and do it. What's up, Trolley Cat? Pretty early stream today. Yeah, I have some plans a little bit later this afternoon. So I just wanted to make time for both. But thanks for popping in. Hope it's not too early for you, like 6 a.m. or something like that. Okay, now let's pivot over to this other side. So So now we are successfully, we've sort of successfully created this link, right? That's what we're doing. I mean, in the actual simplest case, it just looks like this. The task we're waiting on remembers us, remembers that we're waiting on it. So now this is where the implementation is going to get very different. Because now we no longer, I'm sort of thinking about this in real time, but we no longer have this sort of like global checkpoint in the scheduler where we just go and update like everything. The idea in this new implementation is that actually the destroy task event or the task exit API is going to somehow be responsible for making everything runnable again. And it's time for a 20-second stand up and stretch break, so feel free to join me. Right. Trying to work on my posture also. Okay. Yeah. So we need to figure out exactly how this is going to work. So as on a conceptual level, at some point this thing is going to exit. And that's the point where we sort of want to like notify or something, or mark this task back into a runnable state. And I think it probably makes sense to do it here. Just to refresh our memories about how task exiting works. It's sort of like task is running, task exits, and then task exits, which marks itself as exited and then nulls out the current task pointer, which is kind of interesting, as exited. However, task cleanup doesn't happen here because one thing the task cleanup needs to do is free the stack, but the thing is we're still running on the task stack at this point, so it's sketchy to release that while we're running on it. And so that's why I have this deferred cleanup implementation where we don't free all the memory here in this call. We do it on the next scheduler schedule, and so we keep track of this p exited task to destroy. And then after a new task is selected and we switch onto its stack, we then can safely destroy the task. Bird cleanup on next scheduler tick, as I'll call it. Cleanup after selecting next task and switching onto its stack. So this is sort of how task exiting work. Yeah, my posture is honestly effed pro max. Thanks for the reminder. Dude, I'm with you. I feel like I've just been leaning over a desk for like a decade, and it's not good for standing up straight. So I'm trying to be a bit more conscious of that. I feel so like I watch my streams sometimes and I'm like, oh my gosh, what is going on? Like I'm like curved over like crazy. So I'm just trying to be conscious of that. Right. So here's the life cycle of the task exit. And so task exit. Sorry, basically just this. And so task is running, cause task exit, next scheduler ticket gets cleaned up. But as far as any observers are concerned, I think this is the appropriate time to wake any observers or waiters, I'll call them. So I think this would be the appropriate point. I don't think this is really kind of an implementation detail. So yeah, let's just go with this. And so yeah. Afnan, what is up, dude? Good to see you. Thanks for popping in the stream. Yeah. Cool. I'm just trying to, yeah, so let's just implement this. So we need to go to task exit, which is the exit point. Messing with ChatGPT, lol, didn't see the notification. I feel like Afnan has got to be one of the most AI pilled developers I know these days. Definitely in the Discord, I think Afnan is definitely the one using AI the most heavily, which I think is awesome, by the way. I think I've been trying to learn it a bit more myself. I think I'm still kind of a beginner with how to really use agents and stuff like that. Let's just do it here, maybe. So I'm also going to snooze the notifications, but snooze the suggestions. So we like the most basic version of this is going to be, we're exiting now, time to wake up all the waiters. Yeah, and so in the simplest version of this, it's like, but actually, MP, we sort of need to technically do it here, I guess. For auto waiter in MP current task waiters. Like, it's not necessarily that complicated. It's just sort of like, okay, we know that we're exiting. We know that all these waiters here don't need to be waiting anymore. So they can become runnable. So the question is, what are the advantages and disadvantages of this approach? But I mean, even before we get to the, let's just even see if this works. But if we just compare, I think it's really not that much code. Like, again, we can just kind of compare the old way and the new way of doing things. And so in the old way, we are recording a task that we're waiting on. We're waiting on this task to exit. And then every so often, we're like looping over all these different things. And we're checking if this task has become an exited state, at which point we remove it from the list and mark it as runnable. So I guess, yeah, one thing we're doing is, well, I mean, technically we could remove things from this list, but it doesn't really matter because this whole task is going to get destroyed pretty soon anyway on the next scheduler tick. So it, yeah. Maybe it's not necessary. This whole task object will be destroyed on the next tick. So So maybe just don't need to care about that. So off now, it says I burned around 400 million tokens. But look, my codex gives like 90% subsidy. Bro is token maxed out of this planet. That's crazy. Okay. So right, this is like not that hard. So let's think through it then. Is this going to work or not? So just think through it. So wait test creates the task wait for exit. It's going to come in here and it's just going to add this pointer onto the container of this other task we're waiting for, and then we're just going to go to sleep for forever. And then conceptually, the other task is just going to like do a bunch of other stuff, and then at some point, its life is going to end, and it's going to call task exit to kill it, to like die or exit or whatever. And then we're just going to go here. It's going to go through this whole list of people, waiters, and it's going to see that this original task is waiting on it. It's going to make it runnable. And then we're going to go into the scheduler. And then from that point, the waiter is going to be eligible for running. So I am pretty hopeful that this is going to work. And only thing is just making sure that we're no longer engaging this logic. All right, let's just run it. Let's run it. So, okay, we should expect to see the panic, and that's exactly what we see. So, byte wizard, why do you sound like bro code? Who or what is bro code? You gotta put me on. I do not know what bro code is. Okay, so, yeah, dude, that like works. Bit anticlimactic, but that is just another way to implement this thing. And now here's the point where we can compare pros and cons. So let's just talk some pros and cons. Pros and cons, I think. So let's see. A pro of this side is that waking up the tasks is close in the code to where the exit happens. So you can just see that, okay, an exit's happening, and we're going to release we're going to wake up the other things. Over here, it's much less clear. We just have this big global place, and the task exit happens, but the task exit happens over in one place, and then over here is where we update the state of task. And so it's, I would consider that maybe a bit of a con. Again, these things sort of mirror each other. Task exit is far from waking waiters in the code. On the other hand, a pro of this side is that they're semi-global place for all the dating waiters. Maybe that's nice. To some extent, from a performance point of view, I mean, well, another pro is that this is just less code compared to this kind of bigger, seemingly kind of bigger set of code. Downside of this approach is that it's like a bunch of policy and logic that is not strictly related to the scheduler's core responsibility of task switching. And it's sort of this secondary layer around like waiting and waking things up and stuff like this, which feels a little bit like a kind of separate thing. So it sort of balloons the scope of the scheduler. This is just, it feels more targeted And also from a performance point of view, it's pretty efficient. We just like iterate all these things and wake them all up. Certainly we can optimize this implementation and actually have like a list of only things that are waiting. But it's still sort of, we still need to iterate this whole list of things that are waiting every schedule and see if they need to be woken up, where this is like extremely precise. It happens specifically on this particular event. We specifically wake up only the waiters that are relevant. So slight performance advantage, very targeted, simply wake up all waiters. Yeah. What's up, Giatti? How you write code from scratch? I want to learn the skill. How you test if there's a bug or anything? I mean, you just gotta try it. Like, I know if you're growing up in this world where there's AI and stuff, it can feel strange or inefficient to do it by hand, or old-fashioned to do it by hand. But you get a lot out of it. You get much stronger understanding. And if there's a bug, you run the program, it doesn't work, and you figure out why. Team was learning electronics and implement circuits in Minecraft, but I checked out your stream out. Well, dude, thank you. Thank you for joining. Check Brocat out. He teaches programming and stuff. Word. Okay. Will do. Will do. Thank you. Right. So this is sort of my analysis. Basically, all these pros are sort of slight cons. Slightly worse performance. Checking every schedule can be optimized to only iterate through all waiting tasks. But still, maybe that's a lot of linked list iteration to do every schedule, for example. Yeah. So, okay, that was actually surprisingly doable. Okay, just sort of carving out the Git history to remove the noise. Okay. And yeah, so this is sort of the idea. So implement store invert waiting pointers. I don't really know what the best name for this. Maybe I'll say store pointer to waiters instead of waitees, something like that. Nice. All right, so we got a little over an hour left. That's cool. Yeah, now we can try to think about what we would want to do next. So now we have just this really basic primitive for waiting on stuff. And let's see. So we did all this. Did wait for exit. I mean, that's sort of this thing. We could try to do a sleep. mutex is maybe even a bit more advanced. Yeah, maybe let's go. Maybe asleep would be a cool thing to try to do. Yeah. We could try that. I would need to think a bit about how that would work. But maybe that's a nice challenge. What's up, Abuzar? What's remaining in the OS now? Everything. So much. Yeah, basically everything. I mean, anything you could probably think about is not implemented yet. We have some basic scheduling, some basic scheduler APIs. We boot up, but yeah, that's sort of what we got now. Let's think about, let's just, yeah, I don't know. I'm a little bit scared by this topic, but let's just sort of take a baby step towards sleeping. I feel like that would be a useful primitive. So the idea would be something like, actually, wait a sec. Have we done enough testing? I think, I think actually, I mean, testing is sort of a bit bigger topic, but I want to actually add a log here for this case, already exited returning. So what I want to do is, I want to trigger that. And I think the way I can trigger that is I can just do yield. So what I want to do is this task creates another task. And I want to make sure that by the time we call this wait for exit, the other task has already exited. And the way I can make that happen, posture check, is I can call yield here, which is going to trigger the scheduler. There's not that many tasks, and so this thing is going to be here. It's going to start an exit. Which means, I mean, when it exits, this thing hasn't even started waiting yet because it happens here. And so this thing will just get control next, and then we'll go to wait for exit, and the thing has already exited. So I think we should, so if I run this, we should just see some prints where it's like, we see task blank started and exiting, and then we go here, and it should hit this if and just simply return, and then hit the panic. So let's just make sure that works. Yeah, task 1. Task 2 already exited, returning, then the panic. So that's just a bit of a test for completeness that this little check works. Because it's important to think about edge cases. And I think, I went through that kind of quickly, but I don't know if I necessarily thought about all the edge cases super well. All right, edge case. So let's talk about, well, what's the happy path? The happy and expected path is task waits on other task. Other task is running still. Task exits at some point, wakes up the waiting task. It becomes runnable again. That's the happy path. And then what are the unhappy paths? So one is like the task waits on a task that is already exited. Oh, another time for a stand up and stretch break, feel free to join me. See if you have some questions in the chat. Good luck, bro. Thank you very much. Why not using Go or Rust? Short answer, I just don't know either of those languages. I mean, also I think Go is not really designed to be a kernel development language. First off, Rust is, but I don't know Rust, and I don't want to learn Rust right now. Okay. Right. So like, what are some weird unhappy paths? We're waiting on test that has already exited. So we just checked that this is safe. Okay. This works because task checks up front before yielding. But then the question's like all these race, it's race conditions, right? It's like all about can things race against each other? And in my stupid little test, I haven't tested any of this. Yeah, when you're developing in a kernel, it's all about like what kind of race conditions can exist. And yeah, it depends on how much parallelism or concurrency you have in the kernel. What I'm actually realizing is this part is interesting because I'm like checking if it has exited and returning, but yeah, I mean, so before we even dive too deep, the races, it's like, what if the exit and wait happen at the same time? Then the question is like, okay, so what would be necessary for that to happen? And what kind of same time means. And so in order for that to like really happen at the same time, I think you need either one of two things. One, you're going to either need on single core, you're going to need arbitrary kernel task preemption, or on multi-core, this is just simply possible. This is just naturally possible to have two things that happen at the same time. And if either of these are true, that opens a world where one task can be calling wait for exit while the other one is calling exit at the same time, and they race against each other. And so the race is like, okay, let's say we check this thing, the task is like not exited. It's also interesting, like, do we need to, is it even safe to just access the task like this? Is there some kind of lock we need to hold? Not currently, because I don't have any kind of concurrency yet, but in a future world where I would want to have concurrency, yeah, can I even access the task? Because another thread could be accessing the task and mutating its state. So yeah, that's the question. It's very possible that this code is kind of broken and only works on simple single core non-preemptive setups. But the example race would be like, okay, let's say this thing, we check if it's exited And let's say at this point it's not exited. Let's ignore the question of whether it's safe to access this task in an unlocked way. It's not exited. And so we go here. And then it becomes exited. And then something else is kind of racing it, and then it becomes exited. Well, that's okay, right? Because that's what this branch is expecting anyway. Or, actually, no, wait a sec. So, actually, no. So that's the race, right? This branch is expecting that the task is not exited, and there will be some future exit event that will wake us up. The race is what if the task exits here? After we already did this check, we will go to sleep, but the task exit event will already have happened, so we will never be woken up. So that's an example race, right? We're just straight up going to go to, we're even going to access a task that has exited, which is even not good. So, problem, we will access a task that has exited. So that's already not great. And so, that's kind of what I'm talking about with kind of stuff. And so that's just this whole big deal of like race conditions in the scheduler. And I guess the question for right now is, do I even need to care about this? I mean, this is definitely a problem, but it's only a problem, like I said, if we have basically like preemption, like the appropriate level of preemption such that the other task could run here. And maybe one thing is I was disabling disabling interrupts here, which is my shorthand for disabling preemption right now. And maybe the simple solution is like this thing just needs to be up here, because the idea is that disabling interrupts / disabling preemption, by definition, it disables the ability to be preempted in the middle of this code. And so, so maybe the solution is just to move this all the way up here and just strictly follow this rule of like any entrance into the task API of the scheduler leaves the normal schedulable like kernel task application layer and drops into the scheduler layer, which is not preemptible, because the whole point of the scheduler is to provide this foundation for scheduling and preemption on other arbitrary tasks, but the code in here is a bit special. And so let's just imagine if this were the case. And so basically this sort of just kind of locks things up, or like in a good way. Like, so now we come in here and we basically grab a lock. We conceptually just grab a lock over things. And so we come in here and it's now no longer possible. I guess it depends on single core or multi-core. On single core, it's no longer possible for us to get scheduled out. And then like after this point, let's say we do the check, it's not possible for us to get scheduled out and then the other task gets scheduled in and does an exit right here, because we have basically this conceptual lock. And so just whatever the state is on entry is the state that we can rely on. And so if that's true, then we've checked if the thing is exited or not, and we can be confident that at this point it is not exited. And we can be confident that we can safely put ourselves to sleep knowing that the future exit event will strictly be in the future. It won't weirdly happen like right now and leave us in the dangling state. That's my current understanding. The exception is, I don't know. So that's with single core. Let's talk multi-core. Even with multi-core though, I think the scheduler, I mean, ignoring like really advanced implementations, the scheduler basically is a preemption-free zone. And so even in a multi-core world, so the situation would be like one task is waiting while another task is on a CPU that's exiting, another CPU that's exiting. This task comes in, disables preemption. But, you know, honestly, I'm getting a bit out of my league. I don't have strong enough understanding. I think, yeah, in the multi-core world, I think maybe that you need to grab a scheduler lock or something like this to prevent this race. So, yeah. So Cosmic, just vibe code, bro. Honestly, that's a good idea. What's up, Nico, on the Twitch chat? Auto cures see this most useful real life for 50 years. Redundant. Gained utility in C23. Arrows repurposed for type inference. C23 is type inference? That's wild work. Wow, I did not know that. Okay. Let's take a step back. So I think what my takeaway here is, okay. Moving the CLI up to the top, prevent the race. However, more thought is needed for multi-core. We'll handle that when we get to that bridge. For now, I am not going to overcomplicate things too much by thinking about multi-core, I think. Or even necessarily this stuff. So yeah, let's just go with this for now. So I'll leave a comment here. Yeah. Preemption is disabled because if another task, if the task to wait for exits between the chat, and the yield, we will never wake up because the exit event will have already happened. Yeah, that's a good comment. Okay, cool. Okay. What's up, Prism? How are you able to do this? Like, do you stream daily or weekly once? I definitely do not have time to stream daily. So yeah, I stream once a week. Once a week, which is about the time that I have for this. So now, yeah, and so we were just doing some testing, right, with the yield here and just observing that the task already exited and returned, and then we hit the panic. Okay. In the final 45 minutes or so, let's think a little bit about sleeping. So, for example, I like task sleep, and there's like some number here, something like that. A task can maybe sleep for a while, which sort of opens up a box of worms a little bit, because now we sort of need to think a little bit about time and stuff. So that is a question, like, yeah. So let's just start to design this. How would a sleep API look? What would be the simplest kind of sleep? And so I can tell you what the hardest or not simplest would be actually trying to really do something with clocks. Really do something with clocks, date, time, with the was it RTC chips, like real RTC, yeah, real-time clock chips is what they're often called. And so to me, that sounds very not simple. To me, what sounds much more simple is something like the CPU level ticks or something like this. Or maybe even, there's the CPU level timestamp counter. And then on another level, there could be like a timer interrupt on some frequency. So yeah. The simplest version would be some kind of timestamp counter based sleeping. But how would that actually work? And so what would that even mean? So the idea would be you can sleep for like 100. Let's just take a look at this instruction, even the Wikipedia. Okay, let's read the Wikipedia first. 64-bit register the number of CPU cycles since reset. High resolution, low overhead way to get CPU timing. The advent of multi-course high TSC cannot be relied upon to provide accurate results. No promise that will be synchronized. Okay, reliable results. Okay. Yeah, it's discouraged. I think mostly they're talking about from application platforms, though. like or application software. What's up? Sup? Prathamesh? I want to watch it from the start. Where should I start? From which week? Where you do your setup. So there's a bunch of different places you can possibly start. If you're interested in my project setup, that's sort of era 2. I would not recommend era 0. Era 2 is a lot of tooling and project setup. We're currently in era 3. Era 1 is more like kind of preliminary OS work I did to learn a lot about OS development, where I was building this OS thing from this MIT course. So that's how you can think about it. All right. Clubs. Why no AI? You can finish your project within days, probably. Learn it by reading its source code. Not really. You're definitely not going to learn it in the same way by reading the code than by writing it out yourself. 20-second break. So these are the options. And so just to think it through, let's say, so this is sort of like, it's like, you can say a number of cycles here, num CPU cycles. It's like, I want to sleep for 1,000 CPU cycles or something weird like that. So that's like a very strange, like measurement of how long to sleep for. But if we wanted to do that just for fun, how would it look? And so in the similar way to any of this waiting stuff, is there's two sides to it. There's the waiting side and then the waking side. And so I'm just gonna think through in real time how this might look. And so let's say we want to implement some API where we can sleep for a number of CPU cycles using the read timestamp counter, which is nice because it does not involve interrupts at all. It's like really low dependency. Yep. Oh, people in the chat. What's up, Ismail? Nice to see you. What's up, vpool? Did I get? Oh, wow. Stay hydrated. Let's go. What's up? Thank you. Prathamesh. I want to make sure I say that right. Prathamesh. Yeah. Thank you for the jewels. vpool, what's up? Mohammed, if we learned computer architecture assembly in C, can we get into reverse engineering and binary exploitation? Absolutely. I would even say these things is the best way to learn those things. So, yeah. I see your message, front end, Hari. I think we'll need to wait a little bit. I'm trying to do this waiting stuff, and honestly, it's not that. I mean, honestly, it's not. This is what it looks like. This is what it looks like at this current point with our waiting code. So it's not too impressive. All right, let's talk about how would we implement an API where we can sleep for a number of CPU cycles. So on the one end, on the wait end, there's the wait end and the wake end. So on the wait end, we're going to need to, at some point, we're going to need to store some information about, store the current timestamp counter at the time of wait, right? So a task is running, and at some point it's going to wait, it's going to sleep for, it's going to call into the sleep thing, and at that point we need to record, okay, what's the current whoa, okay. Vpool with the donut. Thank you very much, Vpool. Really appreciate that. Thank you. Really appreciate you guys. Yeah. So some point we need to save the timestamp counter into some place, and then this other point is interesting. The wake side is interesting, because unlike with like a timer interrupt or something like this, all we can do is pull the timestamp counter. And so that is going to fundamentally affect the level of precision that we can guarantee. And that's where we get into this whole topic of precision for like waiting. You might hear the term like high precision counter or high precision clocks, or like sleeping with high precision. And that's where we get into this whole thing. Here, this would be an example of a low precision timestamp, like sleep primitive, because all we can do is pull. And that means our precision is going to be limited by the frequency that we're pulling, that the system is like pulling at. And currently, in the absence of a timer interrupt or anything like that, we have this completely cooperative system. So really the only reliable like kind of hook point we have to inject this pull is on every schedule. So every time a task schedules, we would sort of like hook that point and then update the waiting tasks in a very, very similar look of how this, in a very similar design of this like global hook point where we go through and we update all the things, update all the timers. So it's not really that useful, but I think it's a good exercise. Let me find a good place for this. Also, let me find a good shape. Cool. So let's just give this a try. It's not very useful, but it's a nice little step forward. And so let's say we wanted to implement sleep CPU cycles. It's sort of the way this is going to look. So let's just do a bit of a baby step. So okay, I'm going to snooze the inline suggestions so it doesn't give me the answer. Cycles, right? And that's cycles. And as usual, we have to do a preemption. And then it's like, oops. At some point, we're going to yield into a waiting state. And at this point, here's probably where we need to read the timestamp counter and store it somewhere. And so pretty much the natural place we're going to store it is into the current task, probably. And so we need to add some state, which I'm not sure. Start timestamp counter or something like this. yeah, the naming is subject to debate. What is the best name for this thing? But it's just sort of recording the timestamp counter when we start sleeping. And so now here's the part where we need to actually figure out how to get the timestamp counter. And luckily, the classic x86.h from JOS has a function for this. I can call read TSC and get a uint64t. Maybe suggests, yeah, maybe should this be a uint64t? Maybe, yeah, maybe that's a slightly better type than a size t is not completely semantically correct here. So pcurrent task start timestamp counter read TSC. And do I have, I do have x86.h here because there's also assembly stuff in this file. So yeah. Okay. So now it's actually good that I didn't delete this file because we sort of want to use this, except I need to change it a little bit because we're no longer using this for this purpose. We're no longer really doing the exited to runnable thing here. All we're doing here is we're trying to check the well actually we need like I wasn't quite thinking we need to store more stuff, and so, or actually no, what we want to do is we want to store the end time, right? We're out here storing. We need to take into consideration the number of cycles that we're waiting for, and so really it's like it's really like timestamp counter for wake up or something like this. And it's going to be this, right? We're going to read the current timestamp counter, add the number of cycles. We get sort of like this future deadline. To wake up at, right? I'm just going to make it super verbose. And yeah, I will also make it an optional because again, we only want to engage this thing. The state is only really relevant when we are when we have an active wait on a sleep that's happening, and so in general we want to express that. So we're going to store this sort of deadline timestamp counter to wake up at. It's this future deadline, and over on this side. Then it's sort of like, okay, our job is just now to check the timestamp. It's sort of interesting. It's like I might just do it here. It's interesting. So just to sketch it out, like, okay, I'm going to snooze the one suggestion so I don't get the answer, so I can use my brain a little bit. So for every waiting task, we want to check. So if the task dot, actually this is right, O, okay. O time. If we have this timestamp counter and the current TSC is greater than or equal to oops. So task is waiting. So, okay, if we have a timestamp counter to wake up and the current timestamp counter is greater than or equal to yeah. Yeah. So what's up, NSG? What's up, Basai? So go to sleep with a current timer and amount of cycles to sleep for record that point. Every so often later, we are just checking, okay, is the current time greater than that deadline time? And if it is, we mark the thing as runnable. What am I missing? Am I missing something? The reason and then it's funny because I could read the TSC right here instead of storing it in a variable, but then every loop iteration, like that would sort of impact, it would change as the code executes. The TSC keeps incrementing, right? And so I thought it might be nice just to have a fixed time that we compare things against. Right, but we also need to clear out. I don't know why my sense doesn't work. To clear out the waiting state because it's no longer needed. Yeah, I tried this a few weeks ago, but this is an example of where it kind of can be useful to store the scheduler state and then this state together somehow. Like right now we have these two things are completely separate, like this enum of all the different states a task could be in. And then over here, we're storing this very particular information that is only relevant to one of these states. And it's specifically the waiting state. But even more specifically, it's like this waiting on a timer state. And because we're storing these two things in separate places, it creates this burden to make sure to keep things in sync and be like, okay, when we when we make the thing runnable now, we want to reset that timestamp counter state. I mean, we could just like leave it dangling there technically, but it might be conceptually cleaner to also reset that state. Otherwise, there's this sort of like weirdly dangling, like stale value from a previous sleep that we might accidentally reference later, even though it's stale and whatever. So, yeah. What's up, Basai? I have to say, watch a couple of your dev videos, and I really like your calm energy, great content. Thank you very much, Basai. Appreciate that a lot. Okay, posture check. So, I'm always super nervous that I forgot something very basic, but that's sort of my impression about how to do this right now. And so, yeah, let's try. Let's try. So, okay, so, I'm just gonna have it do, yeah, it knows exactly what it wants to do. So we're gonna do a print, like printing and sleeping for a bunch of cycles. And then, yeah, and then we'll panic. Yeah, NSG, yeah, I'm doing really noob stuff right now. So I'm just, after we finished doing the waiting on another task to exit, I was trying to think about what another really simple exercise to try for like a waiting example. And TSC is pretty much my main idea of something that could be useful as a simple thing to implement. So yeah. Yeah, I still don't have a timer interrupt. I don't know why I'm putting that off for so long, but I still don't have a timer interrupt. So, yeah. Print for TSC value before and after. That's a good idea. That's a great idea. Yeah. Log current TSC. Okay. I don't know. Why did it, TSC, current TSC after sleep. Right. So the only thing here is, because there's no timer interrupt, I have to have some other way to drive the scheduler, because the scheduler tick is the thing that's doing this checking. And so it's not enough to it's not enough just to have this single test. I think by itself, like I need some other task that is pretty much just yielding in a loop, I think. Which kind of sucks, but I don't really see a way around it, because basically the approach is like I'm polling the TSC to see if I need to wake this thing up. So I'm going to have another task that's just like always yield task, and it's just going to it's just going to always yield itself. It's in an infinite loop, we're just going to sort of spam the CPU kind of. But you know what? Let's just see it fail. You know, before we even do this fix, let's just see this fail. And so what we're going to see is that I'm going to try to do this test. I'm not going to go through any extra effort to make anything on the system that's going to drive the scheduler to pull the TSC. And what we would expect to happen is that this thing goes to sleep and then never wakes up. There's nothing that's driving the scheduler to pull this thing. And so I just, before we even do this fix, I just want to see it break. And the question is 1,000 enough to trigger this? Because actually there's the idle task, but it, idle task, it actually just panics. So it actually doesn't really make sense for the idle task to be yielding in my current implementation, because I don't have interrupts. I don't have interrupts or external events yet. And so if the system gets into a state where the idle task is the only thing that can run without interrupts, without external events, there's no way yielding is going to like change any of the situation. It's just going to yield forever. And so that's why I just made it panic. Okay, I'm just going to, and so actually what's going to happen is we're going to see this panic, because right now my kernel is configured to only have one task. It's going to call this API. It's going to go to sleep, become waiting. Nothing else is going to be runnable. So the idle task is going to run and the idle task is going to panic. So just to be very clear on what I expect, that's what I expect to happen right now when we run the kernel. That's interesting. It actually didn't hit the panic because 1,000 CPU cycles is a tiny amount of CPU cycles. And that's like way too small of a number of CPU cycles. And it's probably like, we record this number and then simply the fact of just like entering this function, going into here, like doing this stuff, eventually going into yield impl, that's enough to trigger 1,000 CPU cycles. And so by the time we get here, it's already been 1,000. So my takeaway from that is we need a much larger number. I have no idea what that would actually be. I would need to do some math or something. I think, yeah, I just know I need, let's just go with a million CPU cycles. Let's go with 1 billion. I don't know, I'm totally guessing. I don't have a great intuition around that, to be honest. All I need is a number of CPU cycles that's greater than the number of instructions that's going to execute after this line specifically. So this is the starting point, and I just need to choose a number that's bigger than the number of instructions that are going to execute through this like call chain, which eventually leads to yield impl. And it's interesting because I'm in a debug build right now, and so that means there's a lot of instructions, which is going to really radically increase the number of CPU cycles that are going to execute. And so that is going to affect the number I need to choose here. Real quick, I just want to ask some kind of AI, does C have syntax for doing commas or large integer constants? I think it does. It's like an apostrophe or something like that, right? Also, I have no idea what kind of model is this. Okay, let's just go with 1,000,000. Again, I am totally guessing, but that's funny that it actually worked, because 1,000 is just too small. Okay, perfect. So what this is saying is that 1,000,000 was enough instructions to be greater than the number of instructions that executes in the time from the sleep on CPU cycles to the next yield. And so that number of instructions is less than 1,000,000. Therefore, when it hit that update function, it did not wake up the task, and it blocked the task, and the task remained blocked. And therefore, the idle task executed, which caused the panic. And so now we can try to fix that. What's up, 6412s? How are you finding using C++ for kernel dev? Guessing you got stuff like RTTI and exceptions turned off, and using ETL? Yes, exactly. I have, it's completely this setup. No RTTI, no exceptions, and using ETL and some other freestanding libraries. And I have to say, I'm really enjoying it. I'm really liking it. It's much better than C for me, because I have a lot of C++ experience, almost no production C experience, or very little production C experience. I'm just much more comfortable with this. And I'm able to use all these nice high-level language features that I enjoy. So I am really enjoying it. Okay, perfect. So now let's take one step forward, and let's add this always idle task, which actually doesn't do anything. vtables don't generate as much CPU instructions as a lot of people assume. So I guess vtable gen isn't too bad. I mean vtables are virtual calls are super slow. But the good thing is that you can choose whether you want to use them or not. Like, you don't have to use virtual calls if you don't want to. And so for me, I don't actually really have virtual calls in my kernel, with a couple exceptions for things I happen to use it in some places, but it's not fundamental, and you don't have to use virtual calls if you don't want to. So yeah. So now what we're going to do is we're going to add this thing, and so okay. Build task. So now we're going to have the two tasks, and our always yield task is not currently going to yield, but it's just going to loop. And the purpose of the always yield task, well, I guess, I was going to say the purpose is to prevent the panic from the idle task. But if we do an infinite loop, then yeah, obviously there's no way for anything else to run right now. And so we would expect to hang. And so actually that's not really going to prove my point. And so I think we actually do need to have the yield, which is going to be basically kind of a full version of this test now. And so we're going to have the always yield task, which is just always yielding. And it's going to provide the underlying kind of like polling. It's going to fulfill the need to constantly, it's going to constantly call the scheduler, which is what we need to check the timestamp counters. And so let's just try it. Let's just try it. I don't know how long or slow it's going to take, but I mean, 1,000 CPU cycles is really, 1,000,000 CPU cycles is still also not really that many. And so we should see some kind of sleep and resume, I think. Let's just try it. So that was super fast. yeah, it went from 3 million or so to almost 5 million CPU cycles with all this code that's running. But it took a couple schedules. But task one waking up due to TSC. So you can see that we went to sleep at around 59, whatever, 3 million or so. And then it actually took like, I don't know what, it's like 4 loops of the yield in order for 1 million cycles to go by. And then task one wakes up due to TSC. And then resumes, which is honestly pretty cool. I'm gonna take a screenshot of that. I'm actually, it's not super advanced stuff, but if anyone has been in the stream long enough, they'll remember me just adding like 4 loops that spin 1 billion iterations just to like emulate sleeping. Like I used to have these crazy 4 loops just because I had no other way to actually sleep. And so this is the very first time we actually have scheduler integrated sleeping. And I don't know why my keyboard is like really going crazy, but I'm just trying to get back over here. No, I'm trying to get back over here. So now okay, so we know that this happens very quickly. I'm just gonna keep guessing some random numbers. I'll go with 20 million. My goal is just to see a human perceivable like sleep and then wake up. So let's just try that. That was also, I guess that was still way too fast. Yeah, I feel like I'm gonna get made fun of because I just don't know. 500 million. There we go. Okay, there we go. And this logging is in the policy is super noisy, so I will comment it out. And so it's still super fast. It's like, but at least it's slightly human, perceivable. And that will be probably the last thing. So that tells me that 500 million is still super fast. Let's do like 4 times that. Let's do let's do 2 billion or so. Interesting. Okay. Yeah, okay, check that out. Keep in mind that, okay, it's panicked and so nothing is like going crazy, but yeah, keep in mind that during that sleep time, the other thread is like maxing out the CPU, doing the yield loop. But of course, that's not fundamental. When we add timer interrupts, then we'll finally be able to like actually sleep in a more intelligent way. But that's cool. Let's just bask in how cool this sleep looks. I'm gonna go with 10 just to have it be really visible. Okay, that was actually a bit longer than I thought it would take. Let's go with I don't know. It's a good. I mean, did 5 times as long. Let's go with like 5 or something. Okay. There we go. Goes to sleep. wakes back up due to TSC. So that's pretty awesome. I'm excited. So it's like slowly, very slowly, the OS, the kernel starts to have some like basic functionality that starts to ever so slightly resemble something you might have seen in other kinds of programming that you've done. So yeah, cool. So we got basic timestamp counter sleeping working today, which is the most basic form of sleeping possible. But hey, a win is a win. Okay. And then in the future we can get fancier timers, interrupts, and stuff like that. So that's gonna be it for today. I do need to get going in a moment or two, so I'll just sort of, yeah, we'll recap, wrap it up. Appreciate all the support. Thank you, NSG. Technology behind our CPUs is black magic, straight up, like actually. So Farhan, I want to build my own OS. Where should I start from? Yeah, I mean, there's a lot of choices. Farhan, MIT 6828 or Harvard CS61 are some good options. I'll get to this in a second. What's next? Are you planning at open source project? Maybe. For now, it's just my little private hobby project, but who knows? Maybe. I built this kernel brick by brick. Yep. All right. What's next? That's a great question. I mean, I could try to do mutexes. Yes, I could. I'm actually very, very interested to do that. The only thing is that I don't really have like a reason to do them yet, because I don't actually have interleaving, or I don't have preemption yet. So I could make a mutex. But I would just need to prototype it in this cooperative world still. Alternatively, I could actually start going down the timer interrupt route and finally get that going and start and finally graduate to like not preemptive, not cooperative, but like, yeah, like finally get a bit of preemptive multitasking, which would actually give me a bit more of a reason to do a mutex. So yeah, I think, yeah, maybe the timer interrupt, like that actually, I mean, it's been a long time and I think it feels, yeah, like a relatively right moment to get into that. We can check the roadmap. So sleep, right? So sleep CPU cycles is officially over the line. Do sleep seconds, we haven't gotten to like real time yet. But yeah, mutex is condition variables. I don't know, semaphores, like apparently semaphores are useful. Stuff like that. Yeah. Yeah. Let's say something like that. I think timer interrupt sounds about right to start getting into, because once we get a timer interrupt, we can start actually doing a bit more of the scheduling stuff. Yeah, the one challenge I have is there's all sorts of these side topics that I also want to do. It actually really annoys me that I have to be like editing this like kernel run function all the time in different ways to like trigger different things. And I would like to have a better way of having some kind of like tests in place where I don't need to be modifying the production kernel run all the time, but like I can like make a little test that triggers a few tasks and tests some things. So my challenge is just figuring out how to build that into the work, because it's a bunch of work to get that testing framework going. So maybe I will do a bit of vibe coding or something on the side, because it's not really the most important thing that I care about. So yeah. APIC SMP. Whoa. I mean SMP. Whoa, that's crazy levels. I mean, personally, I'm not planning to do SMP for quite some time. I think I still, like, I'm not really like an expert enough at single core yet. So SMP adds like a lot of extra locking and concurrency issues, which I can sort of avoid for now, just to keep it simpler for myself. So yeah, APIC for the timer probably, but probably not SMP for now. Yeah. If I want to start with your playlist, should I start from week 1? I would recommend starting from era 1. Era 0 is like kind of weird, and I don't really recommend people watch that one. But era 1 is like starts to be where it gets kind of more interesting. So yeah. All right. I gotta go, guys. I wish you a nice afternoon or morning or evening, wherever you are. And I will do a quick, reminder. I would like to talk to you about your challenges in the world of systems programming, whatever they are, whether they're technical, career-wise, or something else. I would really invite you to just get in touch with me. I would love to talk to you about your challenges so I can learn how I can be more helpful to this community, stuff like that. And so here's my contact information: Discord, Instagram, email. Please feel free to get in touch. All right. With that said, have a great day. I'll catch you later. Peace.